Thank you. Hi, my name is Renata Ferrari. I work at the Australian Institute of Marine Science, and I'm part of the EcoRRAP team, or Ecological Intelligence for Reef Restoration and Adaptation program. I also, from very young, have had a problem with the default, like being told, this is how we do things. I've always wondered, is there a better way of doing it? Can we learn more from this if we look at it from a different perspective? And I think that attribute has stuck with me because I'm usually looking for better ways of questioning the reef and understanding what happens to it. Because before I continue, I'd like to acknowledge the traditional owners and custodians of the country where we meet for the Reef Resilience Symposium and workshops here in Cairns. I pay my respects to their elders, past, present, and future, and the future leaders of tomorrow. I would also like to extend these acknowledgements to all Aboriginal and Torres Strait Island traditional owners and custodians of the land, seas, and waters where EcoRRAP and AIMS researchers and collaborators live, work, and conduct our research with full, free, prior consent. So I'm not going to dwell too much on what is EcoRRAP because there's been some really, really good talks, Katerina's yesterday and Chris's at the beginning of this session today. But in a nutshell, EcoRRAP aims to quantify natural rates of recovery and adaptation in response to global and local changes, as well as rates of recovery in response to interventions. In other words, our objective is to optimize interventions by understanding the how, where, and when of natural reef recovery. So while we're not doing active restoration interventions, our team aims to inform how to best succeed at those interventions through understanding the ecological context behind the interventions and in the reefs and the locations where the interventions happen. So hopefully this works. Recovery, this is a video I'll start in a minute, but recovery trajectories are not only influenced by the individual demographic rates that happen in the reefs, the identity and relative contribution of organisms in the benthic community also drives differences in recovery trajectories. This can be associated to the innate properties of each species or their traits and or their immediate emerging properties. As reefs recover, it's really important to understand not only the distance between coral colonies, but also how this varies in 3 dimensions. Reefs are 3D, not 2D. And the key demographic gaps in knowledge for coral colonies are huge. I mean, we think we understand the growth of Poraites bommies really well because we have about 300 corals cored over time, and the cores are about this size for colonies that are really big. We know a lot already, but there's a lot more that we need to understand. Using 3-dimensional models, we can tackle some of these questions. And I think this conference's most popular image is one that was done by George Roth from CSIRO, which shows a large area of reef before and after the bleaching event around Lizard Island, I believe. There's lots of amazing images that are coming out from reefs, some from underwater, some from drones, some from satellites. Technology is there, but there's still a gap in terms of how do we extract knowledge and turn that into advice to understand how to do things better and how to boost the success of reef restoration. Well, that's where I thrive. I like figuring hard problems out. So a big part of my job is to figure that out. How do you actually turn that image into information and intelligence? So this is the EcoRRAP study design. As you can see, we have about 12 to 19 reefs, depending how you count them, all the way from the south in the Capricorn Bunkers to the north in the Torres Strait. We have reefs inshore and offshore. And we were really, really interested in complementing the long-term monitoring data with knowledge and data of what happens within reef, how these dynamics and the different key indicators, like the ones that Manu talked about today, change in different sites around the reef and with the depth gradient. And that's what our design tackled. We have reefs we have sites on a given reef that are spread around the perimeter of the reef. They cover 4 key habitats, and that's they vary with wind exposure. So we have front reef, flank reefs, which intermediate wind exposure, and back reefs. And we also have some sites on the lagoon. And we also have sites in shallow and deep reef slopes, and I say deep because we only go down to 15 meters. So it's still all within depths that restoration would happen, but we do know that there's quite a big difference in terms of the light and other processes that happen ecologically speaking between 3 meters and 15 meters. And that's the range that we look at. So at each of these sites, this is how a site looks. We have 4 high-resolution plots, and that's the data that I'm going to talk about today. Each of those plots are about 72 square meters or 12 by 6 meters, and we image them using high-resolution off-the-shelf cameras. On top of that, we have GoPro plots, which are about 100 by 10 meters, and that's what you're looking at the screen right now. These are just imaged with off-the-shelf GoPro cameras, and we can get 3-dimensional and 2-dimensional maps, like the one you're looking at right now, that are about 1 centimeter in resolution for the GoPros. The DSLR plots give us resolutions of sub-millimeter, about 0.03 millimeters, I believe. And this is how one of those high-resolution plots look. So again, beautiful photo. This one's actually lower resolution because it would have been too slow for the screen to display. But what we do is we use machine learning and a lot of person time initially to train the machine learning algorithms to outline the corals of interest. As you can see, not all the corals are outlined there, only the most common ones, because the training does take a huge amount of effort and person time. So we have one fully dedicated staff she's a benthic ecologist, and she has put a lot of time in training this machine learning, but now we can automatically detect 11 of the most common coral taxa, which actually represent about 55% of the coral cover in our entire data set. And once we have those maps digitized, this same benthic ecologist goes down and verifies a subset of those corals, makes sure that those are the species that she's attributed from the images, because as many here might know, not all coral species can be reliably identified from images. Because of that, we have a mix of coral species for those that we're confident about, and genus or morphotaxa, which are, for example, tabulate acropora, because we're not confident that we can identify the species from the images that we have. So what have we learned after 3.5 years using this amazing data set? I'm going to talk about a few highlights. The first one is the distribution of the most dominant corals across the Great Barrier Reef and the Torres Strait. So who are the most common dominant corals across our entire region? There was no big surprises there. There's some massives, like massive Porites, Goniastrias, and Platygyras. There's also what I've termed tables and thin branching corals, mostly acroporas. Most of them are acropora corymboses and acropora tables. And then we have what I've termed thick branches, which are mostly in the Poecilopora family. But in a minute, you'll see that the acropora digitate corals are very similar in size to the Poeciloporas, and they also behave quite similarly in some regards. So this is really important when you're trying to parameterize ecosystem models and understand what's going to happen with different impacts and what to expect from these groups. So where are they? I hope you don't get intimidated by this plot. This is simply showing what the latitudinal gradient of those different dominant corals is. This is data from 2021 to 2022. All of this data comes from about the same 6 months across all of our sites. And you can see there's variation, but the most interesting part, if I can point, is the inshore reefs. So this will be our southern inshore reefs, or Keppel Island. And this one here is our inshore central or Palm Islands cluster. And you can see that they have a lot less corals, in big summary. And also you can see for Porites massives, there's an important decrease from north to south. So there's more Porites massives, a lot more dominance of Porites massives in the north, in the Torres Strait, and in the central compared to our southern reefs. And this is a similar graph for wave exposure, or the wave exposure gradient I was talking about before. So again, you can see how the most exposed reefs or front reef slopes, both deep and shallow, have more corals than the least exposed reefs or lagoonal reefs. But there's a fairly obvious gradient. You have to remember this data set is comprised of more than 20,000 corals. So it's huge variation. And just being able to pick up these patterns at this level or this scale is pretty incredible. We also looked at about 12 different environmental and biophysical predictors of what determines the abundance and the prevalence of these 20,000 corals. And I'm only going to tell you a little bit about the most important ones. So the most important ones was the depth gradient between 3 and 15 meters depth, water clarity, and temperature. This plot has triangles for abundance and circles for prevalence, and blue is good, so that means that there's more of. And red is bad, that means it's less of. And you can see that dashed line is 0. So anything to the left of that dashed line would be red, and anything to the right would be blue. And then anything that's kind of faded out, like for Platygyra in the middle there, is overlapping 0, so it's not significant, or there was not an effect. So for example, in this case, we were comparing deep and shallow. Deep is anything below 10 meters or 9 meters depth, and shallow is above. And we can see that Platygyra is equally abundant and prevalent across the depth range we studied, but all other corals, there's more prevalence and more abundance of corals in the shallow areas of our reef slopes and lagoons. And then temperature and water clarity were also important, and I was really interested to see that for juveniles, thank you, that was also important. Water clarity was generally good for corals. 6 of our 9 taxa were more abundant and prevalent where there were clearer waters, and temperature had contrasting effects. Some corals preferred warmer waters, and some corals prefer cooler waters. The second bit of results I'd like to brush over really quickly is growth and survival. So we looked at the growth and survival between 21 and 22 for our corals, only for a subset of them, so about 10,000 of the 20,000. And we found pretty much that for coral survival, there's a huge difference. You have to remember, this is a year without disturbance. And there's a huge difference between our 3 different groups of corals. So fine branching Ecological tables and corymboses are the most likely to die. Here, along the y-axis, the closer you are to 1, the more likely you are to die. And then the massives are the least likely to die. Initial area was everything. Size matters. The bigger you are, the less likely you are to die. And temperature was also important, but interestingly, it wasn't like the cooler waters or the hotter waters were better or worse. Temperature within our range explained about 12% of the variation in mortality. And the ideal the ideal temperature range was between 25.5 and 28.5 degrees. So that's the ideal for the corals that we're studying in our spatial range. And finally, for growth, size was also extremely important. It explained, depending on the taxa, it explained between 40 and 70% of growth of adult corals. These are corals between 5 centimeters and about 1.2 meters. There's some that are bigger, and this is in diameter. We actually measure the size of corals in centimeters squared, so the area. But I have, just for people that are used to thinking in centimeters diameter, I have written the equivalences up there. For the thick branching corals, so Poeciloptera, Stylophora, and EcoRRAP digitate, we can see that they only get to about 50 centimeters in diameter, but still, the bigger they are, the faster they grow. For Goniastras and Platygyras, we have the same trend. For Borealis massives, it's gradual and it just keeps increasing. And this does not agree with what we know about Borealis massives. Borealis massives, from core measurements, don't seem to grow faster as they grow bigger. But when you actually measure their planar area, they do. So there might be some really interesting lessons there. And finally, the ones that I found the most interesting are the EcoRRAP corymboses and EcoRRAP tables, especially because there's an inflection. When they're really small, they grow really fast, and then they keep growing faster as they get bigger, but they kind of stabilize a little bit more. So there's a point where they will kind of put more energy into other processes, like reproduction potentially. And the size, so size is important, size matters. Are there any patterns or changes across our entire study design in terms of the size frequency distribution of these corals? In short, because I'm short with time, but you can come and talk to me later, there aren't many. There's a little bit of a trend. Inshore reefs seem to have larger corals compared to offshore reefs, but we couldn't find any evidence. The size frequency distribution of our most dominant corals And that you can see that because there's overlap in between these histograms across all of our clusters and across our inshore and offshore reefs don't really separate. So corals seem to not have a huge difference in size frequency distributions between our different habitats, our different depths, our different inshore, offshore, and our different latitudinal gradient. So how does this translate into restoration? Well, when you're choosing the right environment for your right taxa, you definitely need to think about survival and growth, and you need to know what the right place is for your corals. So we can use this information to answer questions like, do flanks have more corals than other habitats? What are the dominant taxa in different habitats, different depths, water clarity, etc.? So we produce species distribution models for each of these taxa. And if I zoom in into just one of them, I can do a little recommendations or tips card. So there, yellow means there's more higher density or more abundance of these corals, and purple or dark blue means there's less. So you can see that for massive poraides, they prefer the edge of the reef. So they prefer narrow ranges in temperature. North is better than south for massive poraides. They also peak up to girth at around 2,000 centimeters squares or 50 centimeters in diameter, and then they steady increase in growth rate with size up to 10,000 centimeters square or 112 centimeters in diameter. It is important to note that our plots are only 72 square meters, and I don't think we're capturing the really, really, really big massive poraides. That's work to be done with our GoPro plots, but we don't have that data yet. Probably the biggest coral that we capture in these results is up to about 2 meters in diameter. And they prefer low exposure and shallow habitats. On the other side of the spectrum, we have Corymbus acroporas, and I'm gonna just quickly click through that because I'm out of time. And then in terms of survival highlights, we also have these key bits of information. So which taxa are better at surviving? What's the size that they survive best at? What's the percent cover that they will do better at? That one's a really important one. There's like an optimal percent cover. And then what's the ideal temperature they'll survive at? And for growth, we have similar information coming down. And with that, I'm going to say thank you, and sorry for going over time.
Super quick question. Okay. Renata's very passionate about her work, so you should catch up with her in the lunch break. Can we invite Tanya now